Hey, good morning, everyone. Welcome to the Data Gold channel. It's been a while since I posted, and I'm in the midst of rebranding. But I wanted to kick off the video series here. Haven't done one in a while, but really wanted to kick off one here with a doozy. One of the things that we're going to feature as we do these videos is we're going to talk about what is the business problem that we're trying to solve. And today we're going to talk about classification using naive Bayes. And what that is it's an algorithm that basically assumes a strong independence between features. So we're going to talk about features and we're going to talk about how to classify and what naive Bayes can be used for to quickly classify a series of features and do predictions. So the objectives today are to show how to display an image in the Jupyter Notebook, to introduce Bayes theory as an analytical method. We're actually going to skip over the distribution part. I'm going to cover that in a later video. I'm going to show you how to use random numbers and to create a series of arrays, create those or convert those arrays into a data frame, convert that target variable to a binary value for analysis, check for balance in the data set. And again, in a later video, we'll show what to do with an unbalanced data set. We'll run a baseline model using naive Bayes. We'll show how to measure the performance of that model and then how to improve the model. So I love to go out and to find old books in a lot of times antique stores. And I found this particular one called Star Rouge. So I'm going to show you here. This is, you use this IPython display to import an image, and you just run that and you get the image. So the image has to be stored in your working directory. But this is the book called Star Rouge. And this is actually a nonfiction book and is a little scary. When I read the book, basically in 1968, when I was very young, the Soviet Union, or there was a Soviet sub that attempted to launch a nuclear missile somewhere near Honolulu, and the speculation was that the target was Honolulu or Pearl Harbor, and basically where I got interested in showing this approach using this book was in the book. They cover how they essentially use naive Bayes to do this calculation to determine basically a couple things. One was apparently there was a self-destruct mechanism that had been worked on with the United States and Russia. I guess Eisenhower gave it to the Soviets to use in their subs. And the theory is that it was a rogue element, whether it was the KGB or somebody inside the Soviet government. But essentially, they were trying to determine using Bayes if it was a rogue launch or not. So what I came up with here is totally fictional in terms of the actual analysis. The factors are real based on what they explain in the book, but how they did it is still classified to this day. So basically, again, when we show Bayes here, what we're really looking at is if you want to know, you're trying to figure out the over on the left-hand side, the probability of A when B has already occurred. So what you know is the probability of B when A has already occurred, the probability of A, and the probability of B. So let me give you a practical example. Let's say that your company receives thousands of emails a day and you want to filter out spam emails. So you notice that through your analysis, you know that 10% of all emails you receive are spam. You also know that of the emails that are marked as spam, 80% contain the word discount. And of the emails that are not spam, only 5% contain the word discount. So the question becomes, if an email contains the word discount, what is the probability that it's spam? So using Bayes' theorem, that would be P spam probability of spam with discount equals the probability of discount spam times the probability of spam divided by the probability of discount. So basically, if you run through this, what it ultimately tells you is that there's a 64% chance that if the email contains the word discount, it's spam. And you could run this for multiple words and do this analysis. But in this particular case, again, we knew that there was a 80% chance. So you're trying to figure out you don't know that probability of if it has the word discount in it, if it will actually be spam. And this is just one example. So in the book, they talk about there's these 8 factors that they use to determine whether or not the sub or the launch was a rogue launch. The first one was the type of damage to the substructure. So there were really 3 different choices. The first one was a missile launch where they assumed a missile was launched. Another way that battery could have been damaged or the sub could have been damaged was battery leakage. And then the third one was other. And we used equal probability for all 3 of those. The second one was the placement of the damage. So they knew that there were 8 compartments in the sub and there were 8, again, equal probability. The third one was the geographic coordinates at the time of the sinking. So point K was where they lost track of the sub because we track all their subs even back then in 1968. Point 2 was in the patrol box where they were assigned, and then point 3 was the actual site where the sub sank, where the launch occurred and the damage occurred. The fourth factor was the proximity to latitude, longitude for a missile launch. So there was a 70-30 probability, 70 yes and 30 no. The sub had to be the way that the nuclear launch worked at the time is it had to be at a major intersection of a latitude, longitude. The fifth one was the location where the crew members' bodies were found inside of the wreckage. So based on where they were actually found, the compartments 3 to 8, there was a 12% chance. And then compartments 1 to 2, there was an 88% chance. And when the crew members' bodies, what the theory was is that this rogue unit imprisoned all the actual crew in compartments 1 and 2. The sixth factor is the SOSUS tracking. These are the buoys that are out there in the Pacific Ocean, or I guess in all the oceans, but there's 14 different buoys or 14 different days, and again, equal probability. The seventh factor was radio interceptions. So there were 6 days where they were intercepting the radios, and again, equal probability. And then the eighth factor was the satellite data. So again, a fix from the satellite that they use to track these things. Again, 14 different days. So there were 14 different equal probabilities. And then the target was whether it was a rogue launch. So a 1 was a yes and 2 was a no. We'll use a 50% probability for the first go around. So again, the factors here 1 through 8 are real. That they're real factors. But how you're going to see how I ended up combining them is a total guess, or not even a total guess, but I just wanted to show it to illustrate the Bayes theorem. So again, the difference here is that in the example, we've really only had the 2 probabilities, the 2 factors, and then we figured out the probability of that overall probability by combining them. In this case, we're combining all 8 of these factors. So we'll bring in our libraries. And then you can see here what I did is based on, and this workbook will be in the GitHub for the YouTube channel. But you can see here what I did was I'm going to generate 1,000,000 rows, and I'm going to use the probabilities based on what I said above here. So for example, here we said there were 3 different factors or 3 different levels of this damage factor, and I'm going to use equal probabilities, and that's what I blow out down here and show how to do that. So in this case, I'm creating individual arrays for each factor, and then so I'll go ahead and create those. You can see it does it very quickly for random. Again, these are random numbers, and then I'm going to create a data frame. So now I'm going to combine. I have all these 1,000,000 row arrays, and I'm now going to create this frame called Red Star. So when I do that, I'm just going to show a quick heading here. And what you may have noticed is the target, and this is where I took a lot of liberties. The target, all I did was multiply all those factors together. That's probably not the way they did it or necessarily the best way. You can see I played with some other ones here, but for the most part, I'm just doing it to show how to use this model and this algorithm and then how to improve on it. So you can see here, one of the weird things you'll see right away is that because I'm multiplying all those factors together, again, this is just the header rows, the first five, I'm going to get some weird numbers in the target. And when I show the description, you could see here, that there's a mean of 453 with a standard deviation of 723 at, and the maximum of 47,000. So we're going to have to do some work on this to be able to do some analysis. And when I did the box plot, you'll see it's very that target has a lot of outliers, a lot of outliers. In fact, you can't even read it. So let's just drop the target and we'll take a quick look at what it looks like without the target in there. Again, it's a lot more reasonable. And when I run this, you're going to see that without the target factor in there, I get a little bit more resolution around my factors, and they're all relatively close together because of the way that I chose them. So you'll see here, there's a section in the notebook around distributions. Now, when we get into the model, what you're going to see is we use a Gaussian distribution, which basically means we're assuming that the data is normal. The proper way to do it would be to check the column distributions. When I did check them. This takes a little while to run through this, so I'm not going to show this in this particular video. We're just going to assume that they're normal. The other thing we want to do that we're going to do here is we're going to convert those weird values in the target. We're going to say that if it's more than 100, we're going to convert it to a 1, and if it's less than 100, it'll be a 0. So when I do that, and when I run the header again, I'm going to see here now, all that's going to show up in the target are zeros and ones. Now I used 100 as a cutoff. I could have used another number if I want to go back and balance the data set. But again, that multiplied factor it's just really make believe. So we'll just stick with that. And then this is just a bar plot showing the what does it look like? You can see here, there's a lot more zeros than there are ones. And this just shows the XX will just shows me that I have 806 zeros and 193,000 ones. And if you remember from my factors up here, this is, the one, in this case, it's a 0. It really should be 0, but the 0 is it was rogue, and the 2 was that it wasn't rogue. So when I come down here now, I'm ready to start running my models here, my Bayes models. So the first thing I'm going to do here is I'm going to run using scikit-learn. I'm going to do my train test split. And this is where I'm going to take basically 66% of the data is going to be my train, 33 would be my test. So we'll go ahead and run that. And again, we're assuming this Gaussian, and what you'll see in scikit-learn, there's about 6 or 7 choices for naive Bayes that you can run, again, based on the distribution and how the factors are set up. We're just going to stick with the Gaussian for now. And when we do that, this is what we can see here, that this is the formula for figuring out this is what the algorithm's actually using. So we're going to go ahead now using the train test split that we did. Using the train test split that we did here, we're going to go ahead and run that model. And then what we're going to do here is we're going to import my accuracy score, my confusion matrix, my F1 score, and a report. And what this is these are the numbers that we use to determine how good the model is. So we'll go ahead and we'll run it. And you can see here we get about a 69% and a 66% for the F1 score. So in this particular case, that's okay. It's not wonderful. It's not great. But for a first go around, it's not too bad. So when we look at the confusion matrix, it shows us that these are the errors. So this predicted, in this case, the model predicted at 164,000 were rogue and in this and correct predicted correctly. These are the incorrect ones. And then not rogue, it's 64,000 versus this very small number here that it predicted wrong. So again, if we go back to the objectives of this particular video, we say, okay, what was the one of the objectives was how could we improve the model? So one of the things you might do is you might run a correlation to see which factors are correlated. And when I look at this, I really don't have anything that's super strong. One being highly correlated. Um, and in this particular case, we're going to pull out this one factor here, the geographic factor. So what we'll do here is we'll go back up to the top and to this one here. And what we'll do is you'll notice that here I had commented this out, but I'm gonna take this one out and I'm gonna comment this one now. And what this is going to do is it's going to drop that geographic column. So when I'll run through all this again. You can see here now this is 45. I'll run it again here. I'll run this one. And right off the bat, you can see I get some improvement based on removing the correlated features. So that's one way to work on it. That's one way to do. You can look and see factors that are correlated, and what you're looking for is that additional factor isn't really adding anything to the model because they're strongly correlated. So when I run this again, you can see this is kind of interesting that even though the numbers went up, um, it's still predicting, even when removing the correlated version, primarily that it was a rogue launch. The next thing we could do to improve our model is we could use what's called synthetic data. And this is a tool within this particular one is from IMB Learn, and it's called SMOTE. And the difference is that oversampling basically duplicates some of the existing data. SMOTE generates new samples by interpolation. So it's looking and it's kind of creating the median and the mean, and it's creating synthetic data. So when we do that, we'll go ahead and do that we'll drop the geographic again and we'll see. We'll run the model. Take a little bit longer. And then we'll fit it. We'll run the predictions. And you can see here we get about a 73% and a 55. So again, it's not as good as the taking out the correlated features. The last thing that you could potentially try is to convert the data frame to log. And again, this technique can be used. Again, this is all kind of made up data and factors anyway. But when we do this here, what we're going to see is that when I convert them to log right away, I get some INF numbers in there. And if I tried to run this now on this data frame, the naive Bayes doesn't work very well. It doesn't work at all. In fact, it'll throw an error. So what I'm going to do here is I'm going to replace those. I'm going to drop anything. First, I'm going to convert them to NAs, and then I'm going to drop the NAs. And again, you have to be careful when you do this because you really, we created 1 million records. If it drops 500,000, you don't want to do this. In this case, I think it only dropped about 100,000. So when we look at it now, the numbers look different because they're log based. And then again, we run this and we fit it. And this just explains the whole, you can't use the INF or NANs, NAs in this type of, naive Bayes analysis. So we'll run our classification report again. This actually shows us it's very high. The accuracy and the F1 score are very high. Again, when I run the confusion matrix here, this is very interesting that you could see that it really not only it got much more accurate, but it also pushed the whether it was a rogue or not rogue to not rogue. So there's actually quite a few reasons for that. But again, we're not here. We're just trying to show, how to run a model and some different techniques. So one of the things you'll see here is that the log transformation is really relevant when the data vary a lot on the relative scale. So if you think back to our histogram, or I'm sorry, to our box plot, it doesn't really make sense because relatively all the data was the same, especially after we converted the target to zeros and ones. The other thing that you can always think of when you do this is maybe the naive Bayes isn't the right model or the right algorithm to run. And in this particular case, we kind of did the same thing here. We said let's go look at this gradient boosting classifier. And when we run this one all the way through, what we actually see is right off the bat, we get a pretty good accuracy and precision there. And then you could see here when we run the confusion matrix, again, we get a very small amount of errors, which are here. This is saying that on the test data, it essentially predicted correctly. And you can see here the results here when we did our baseline. We had about a 69% and a 66 on the F1. We removed the correlated data. It went up to 81 and 84. The synthetic data wasn't that great. And then the log data was very accurate and very, very precise. So again, wanted to just run through this very fascinating book if you get a chance to read it, but also give an example of how you can use naive Bayes. Again, like us and subscribe, and the workbook will be out on the GitHub page. Thanks a lot.